So this is Math 150, Section 2, Lecture 6. What we're going to be doing today is we're going to be doing limits. And eventually we will be seeing the secret of multivariable calculus, the one picture that describes exactly how bad this class can be. All right. How many of you have seen the Epsilon-Delta definition of limits? Right, not too many. I will state the Epsilon-Delta definition. You should see it at least once in your life. We will, for the most part, not do things that rigorously. We will do things more by inspection. Oh, yeah, it's clear that this is the limit. When I was a graduate student at Princeton, I was in charge of undergraduate help sessions for a while. And whenever we got to the epsilon deltas in the calculus class, it was all hands on deck. Get as many graduate students as you can to the rooms that day. So here's the informal definition. A sequence xn converges to a limit L if xn minus L goes to 0 as n goes to infinity. So I'm writing it very informally. As you go further and further and further in the sequence, you're basically getting very, very close to the limit value L. I'll now write it more rigorously. I'm going to introduce some math notation. So the upside down A means for all. So for all epsilon greater than 0, backwards E, this means there exists an n greater than 0 such that for all little n greater than n, xn minus L is less than epsilon. So the way you should view this is I have a sequence and I want it to converge to L. We're going to play a game. You give me an epsilon. You give me a tolerance. Professor Miller, I want to be within 1 over 1,000 of L. And I said, okay, well, as long as you take your little n to be at least this large, take at least the 2 billionth term, from the 2 billionth term onward, everything is going to be within 1,000th of L. And so, actually, being within 1,000th is not quite good enough for me. I want to be within a millionth. I say, all right, let's do it again, and I will choose an even larger value of n. And I'll say, as long as n is at least a quadrillion, we will be within your 1 over a million. And say, well, I changed my mind one more time. I'm young. I'm allowed to do this. I want to be within 1 over. And we just keep playing the game. And no matter what value you choose, I can say, if I go sufficiently far down in the sequence, I'll be okay. You can also do this for functions. And we'll say the limit as x goes to x naught of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus x naught is less than delta, then f of x minus L is less than epsilon. And note, very importantly, x does not equal x naught in these calculations. I'm talking about the limit as x approaches x naught. It is never actually equal to x naught in this calculation. I'm just letting it get very, very, very close. And what I'm saying is the limit will exist if no matter what tolerance you give me, whatever epsilon, I can always find a delta such that if x is sufficiently close to x naught, then the value of my function is going to be sufficiently close to your limit. If f of x naught equals L, then f is continuous at x naught. So it's very important. I'm not saying my function has to actually equal the value of L at that point. If so, then it's continuous. So a picture is worth 1,000 words. Let's draw pictures to what's going on. So imagine here's my function. Here's my point x naught. And here's what I believe the limit should be. You give me a tolerance. So here's L plus epsilon. Here's L minus epsilon. And now I need to show that if I stay sufficiently close to x naught, then the values of my function will be sufficiently close to L. So I've got to be within this little band. So what's interesting is if I'm really close to x naught, I'll be close to L. But actually, if I'm far away from x naught, if I'm in the right spot, I'll also be close to L. The problem is, if I look over here, yes, I'm within the band, but then as I start to move towards x naught, I leave the band. And so it's not going to be true for all values from here all the way down to here. Some of these values will still be close. Other of those values will not. But if I go down like this, and I go down like this, I can say as long as I stay in that small little area, then the value of my function will be very close. And then in a rigorous class, in a real analysis class, you will actually compute, if somebody gives you an epsilon, exactly what delta do you need. All right. So this is the high-level definition. For the most part, I prefer the more simpler, the more informal. I've got a sequence. As n gets very, very large, it's approaching L. Or as x approaches x naught, it's approaching L. So there's a couple of natural questions you might want to ask about limits. So I've given you the definition. What's something you might want to know about limits? So I give you a sequence. I tell you n is going to infinity. You might want to know, does the limit exist? That's the first question you can ask. If the answer is no, there's no more questions you can ask. We're done. So imagine now the limit exists. What might you want to know about the limit? So I want you to get into the habit of asking questions. What would be a good question to ask about the limit? So what about, yes?
Could there be multiple?
I'm sorry? Could there be multiple? Is the limit unique? What do you think? Do you think something could approach two different values? As n gets very, very large, it's getting very close to L, and it's also getting very, very close to L prime. Should you be able to get close to two different numbers? No. So limits are unique. So we can talk about the limit. So if you imagine, here's L1, here's L2. Let's say there's some separation between them. They're not the same number. We're assuming there's two different limits. Well, as n gets very, very large, my sequence has to be converging to L1. It also has to be converging to L2. I could write this up really formally and really rigorously. I think you agree with me that this is a good level to be writing this up. As an exercise, if you want, strongly encourage you to try to write this up rigorously. There's a difference, there's a gap between L1 and L2. Let's say the gap is 5. If I then choose windows of size 1 on both sides, they won't overlap. If the gap between them is 1/10, choose a window of size 1 over 1,000, and they won't overlap. I can choose a really small region about the two that won't overlap. And because it converges to L1, eventually when n is really, really large, I've got to be in here. And because it's converging to L2, when n is very, very large, it has to be in here. I can't simultaneously be in both because they're well separated. So because my bins are separated enough, I have a contradiction. So limits are unique. Okay? The next question you might want to ask is, how do you find a limit? That is much harder. And there are a lot of times when we can only prove that something exists, we can't actually tell you where it is. And this is often quite annoying. So here's a good example. Imagine you are a candidate running for office, and your campaign manager is really excited. They come to you and said, "Good news, we have a winning strategy." What is it? I don't know actually what the winning strategy is. I just proved theoretically that there's a way for you to win. You are not going to be hired again. Right? You need details. But there are times in math where all we need to know is the existence of an object. We don't actually need to find it. So how many of you remember the mean value theorem? One of my favorite theorems from calculus. Right? When we do the proof of the fundamental theorem of calculus, it'll be mean value after mean value after mean value. Wonderful, wonderful theorem. The mean value theorem tells you that if you have a continuous differentiable function on an interval, there is some point where the derivative at that point equals the average f of b minus f of a over b minus a. Or your instantaneous speed equals your average speed. But it doesn't tell you where that point is. It just tells you the point exists. And for a lot of things, it's enough to just know that it exists. It would be wonderful for a lot of things to calculate it, but the existence is frequently enough. So I want to do an example now of a limit where we actually can calculate what it is. It's one of the most important limits there is. It'll allow us to start reviewing some things and preparing for when we get to sequences and series later in the semester. So we're putting some material in the bank. Normally when I prove this, I often prove this with a basketball game. And so when we get to sequences and series, we will revisit this by proving this limit by playing a game of basketball. One thing I do want to quickly remark right now is you may have noticed on the homework problems, there seems to be a little bit of a lag between when problems are assigned and when we cover the material. We've covered the material a little bit before the homework is done. This is not an accident, this is deliberate. I know a lot of you have lives outside of Calc 3, and you sometimes have, something going on Monday and Tuesday night and the homework is due on Wednesday. This way you have plenty of time from when things are assigned, so you can come and talk to me, you can talk to the TAs, you can talk to your friends. You have plenty of time to be working on things. I've posted essentially the homework assignments for the whole semester. There may be some small, minuscule changes in terms of when things are done, but you are welcome to look at the homework tab and move on ahead. Just keep them on separate pages. All right. Geometric series. So let's let xn be 1 plus r squared plus r to the n. So this is one of the most famous sequences in mathematics. If I multiply by r, 1 times r is r times r is r squared. This is fun as a Bostonian. R to the n minus 1 times r is r to the n, and then r to the n times r is r to the n plus 1. I would love to see how this would be captioned if it was an option. All right. If we subtract, notice the massive amount of depth that happens as we walk down. All the intermediate terms cancel, and we're left with just the first minus the last. So we have 1 minus r to the n plus 1. Here we have xn minus r times xn. So I can just factor this as 1 minus r times xn. And so I get xn is 1 minus r to the n plus 1 over 1 minus r. And I can write that as 1 over 1 minus r plus r to the n plus 1 over 1 minus r. And this is a really convenient way to write it. I can now ask, what happens as n goes to infinity? What do you think happens to this term? So what happens to r to the n plus 1?
Goes to infinity.
It goes to infinity. What must be true for it to go to infinity? Does it always go to infinity?
Greater than 1.
So if r is greater than 1 in absolute value, this will go to infinity. If r is less than 1 in absolute value, what will this go to? 0. So if the absolute value of r is less than 1, then xn is going to converge to 1 over 1 minus r. And not only will it converge, we will even know exactly how quickly it's converging. We will know what the error is. So this is a wonderful formula. Now, sometimes you can get some interesting results. What's 1 plus 2? What if I add 4?
7.
Add 8?
15.
15. So it's always 1 less than a power of 2. What if I add all the way up? What if I add all the powers of 2 in the world? What do I get? I get infinity. Does everyone get infinity? I actually get something else. Anybody know what I get?
Infinity minus 1? No.
Close. Just minus 1. It's so large it goes past positive infinity, starts back at negative infinity, and almost makes it all the way back to 0. How the hell am I getting negative 1? Any thoughts as to how I'm getting negative 1? I'm doing something illegal.
Because infinity is fully defined?
No, well, infinity is not fully defined. What kind of sequence does this look like? 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th. It looks like a geometric series. So let's use a geometric series and let's put the ratio in as 2. And get 1 over 1 minus 2 is negative 1. So according to the geometric series formula, the sum of the powers of 2 should be negative 1. Right or wrong? Wrong. Okay? You've got to be very careful when you have formulas. You only use them where they're applicable. The great financial meltdown from 2008-2009, a huge amount of this was due to people using math formulas in places they shouldn't. The conditions were not satisfied when they were trying to use these formulas. And the more bad things they bundled together, amazingly, the better result it got. And you could make something even better by putting in something even riskier. So you really want to be aware of when can you use a formula. This formula works if r is less than 1 in absolute value. I can't use it here. Now, amazingly, in advanced mathematics, this equation makes sense. And there is a way to interpret this where it does equal -1, and that is not nonsensical. But for the most part, what I want you to be very careful about is when you have a formula, always ask yourself, what are the conditions that must be met before I can use the formula? Are they all satisfied? Is my checklist good? And if so, then you can use the formula. Okay, so this is a really good go-to example of a limit that matters and that we can actually compute. So we can actually tell what the limit is. There's a lot of limit laws which you should remember from calculus. Essentially, your formulas for rules of differentiation are consequences of your rules for limits, with the nice twist that the product rule and the quotient rule are painful. Right? If you could decide how math would be, what would you decide the derivative of a product would be? The product of the derivatives. And if you could choose your own quotient rule, the derivative of a quotient would be the quotient of the derivatives, but it's not. So a lot of the rules in calculus come from laws of limits. So limit of a sum diff. So if I have a sum or difference, the limit of a sum diff is the sum difference of the limits, provided at least one is finite. So we want to say that the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. This should remind you the derivative of a sum is the sum of the derivatives. We need at least one limit to be finite. What's infinity minus infinity? Are we allowed to deal with infinity minus infinity? No. Infinity minus infinity is one of the undefinables. What about infinity plus infinity? Infinity, yeah. You have infinitely many dollars in the bank. Your friend gives you infinitely many more. It's a good day. Right? What about you have infinitely many dollars in the bank and your no good friend needs a loan of infinitely many dollars? How much do you have left? Well, it depends. What about infinity times infinity? Can we do that? Yes. Infinitely many friends give you infinitely many dollars. This is great. Right? What about infinity times 0? What does that equal? It's
zero.
not. I'm sorry?
Is it 0?
Depends. It's a fight. Right? So the Karate Kid montage is maybe useful right now. That we don't know which is going to win. So for instance, let's look at the limit as x goes to infinity of x minus x. What does that equal?
Yeah.
0, right? At every moment in time, I have 0. What about the limit as x goes to infinity of 2x minus x? What would that be? That would just be infinity. And the limit as x goes to infinity of x minus 2x, what would that be? Negative infinity. If I try to break this up, is this the same as the limit as x goes to infinity of x minus the limit as x goes to infinity of x? See, this would give me an infinity minus infinity. This would also give me an infinity minus infinity, and this would also give me an infinity minus infinity. And this is why I have to be careful. I don't know which, when I have infinity minus, I've got infinity minus infinity in all three cases. And I get 0, positive infinity, negative infinity. That's why we have to be so careful with stuff like this. The next one would be the product. So if I give you the limit of a product, what would you like that to be? So limit of a product is the product of the limits if at least one is finite. And again, to consider how things could be dangerous is imagine you have the limit as x goes to infinity of x times 1 over x. So what should that limit be? X times 1 over x. What should that limit be? It should just be 1. But if I now give you the limit as x goes to infinity of x squared times 1 over x, what would that be? That'd be infinity. And who can see what the next one is? What's my next example?
X times 1 over x squared.
Yeah, it's great that I'm already this predictable this early in the semester. Wonderful, right? And what would that limit be?
1 over 0.
So what is it? 0. So in all three cases, I have infinity times 0. So infinity times 0 could be 1, it could be infinity, it could be 0. I can make infinity times 0 whatever I want. Right? This just shows you how careful you have to be with limits. What do you think the limit of a quotient is? Quotient of the limits. And for that, I need at least one of the quotients to be finite. Do I need anything else if I want to do quotients? So, limit of a quotient is the quotient of the limits if at least one is finite. And do I need anything else? Yes.
The denominator can't be 2.
And the denominator limit does not equal 0. We're not allowed to divide by 0. Right? So as long as that's the case, then we will have the limit of a quotient as the quotient of the limits. Okay? And now we can start calculating and we can start doing lots of problems. So you've hopefully done some of these problems in a calculus class or maybe an algebra class. And we have a bunch of techniques. And so I'll start with a one variable problem, and then we'll talk a little bit about how things can get more complicated. So let's look at the limit as x goes to infinity of 2x squared plus 4x minus 11 over 3x to the 4th plus 7x minus 9. So I want to calculate this limit. So what do you think this limit is going to be as x goes to infinity? Yes?
0.
Good. Why is it 0?
Because the power in the denominator is
Yeah. The denominator beats the crap out of the numerator. Right? You've got an x to the 4th. It's growing quartically. The numerator is only growing quadratically. To do this rigorously, pull out the highest power of x you can from the top and the highest you can from the bottom. So it would be the limit as x goes to infinity of x squared, and then we would have 2 plus 4 over x minus 11 over x squared. And then down below we would have an x to the 4th, 3 plus 7 over x cubed minus 9 over x to the 4th. As x gets very, very large, what is the 2 plus 4 of x minus 11 over x squared? What does that look like? It tends to 2. What does the bottom parenthesis tend to? Tends to 3. So this part's looking like 2/3. X squared over x to the 4th, oh, that's just 1 over x squared. And what does 1 over x squared go to? 0. So this will just be 0. Okay? And so you can calculate a whole slew of limits like that. I'm not going to write it all down. Nobody seemed to want me to. If you have a vector valued sequence, what's the limit of a vector valued sequence? Well, for that limit to exist, each component must converge. So essentially, if you have a 3 vector, 3 limits must happen. If you have a 5 vector, 5 limits must happen. And all the limit laws that happened before just continue to hold. The limit of a sum will be the sum of the limits. And you just do everything component by component by component. All right. So now we're going to apply the the Karate Kid perspective, right? How many of you remember limits from Calc 1? How many ways are there to approach a point in Calc 1? 2 ways. I go right, I go left, or maybe from your perspective I go left and I go right. There's not that many possibilities, right? Is it unreasonable to ask you to check 2 things? No, right? If you're asked to check something, there's got to be at least one thing to check. So 2 is essentially almost as small as the possibilities I can give you. All right. So out of curiosity, how many of you have seen Karate Kid 2? Has anybody seen Karate Kid 2? So you remember the secret of Miyagi Karate? All right. So here is the secret of multivariable calculus limits. And when I first started teaching this class at Williams, my kids were much younger. I probably violated child labor laws. I had the preschoolers in their class make individualized Miyagi limit sheets for all of my students. All right? That is a path converging to a point. If I want the limit to exist for a function of 2 variables with x, y approaching a point, I must check every path. Is the x-axis a path? Yes, it's a damn nice one. What about the y-axis? Another nice one. What about straight lines? Other nice ones. Is this a path? Yes. You must check this path. There are infinitely many such monstrosities like this to check. This is why multivariable calculus limits are much harder than one-dimensional limits. Left, right, okay? Not that many options. Here, you have to look at all of these paths. We need to find a way to investigate all of these essentially simultaneously because we do not want to spend the rest of our life going all of these case by case by case. Now, the best way to show a limit doesn't exist is to take 2 different paths and get 2 different answers. If you get 2 different answers, we know limits are unique. So once you find 2 paths that give 2 different answers, you're done. The limit does not exist. What if every set of paths you take gives the same limit? Does that prove that the limit exists? No. It just shows that so far you haven't found a difference. It gives you evidence. It might make you feel comfortable. I can give you a function where you get the same value along any straight line and along any parabola, but not on cubics. You can come up with some strange functions. Okay? So let's start looking at a couple of examples and try to get a sense of what's going on. So let's look at the limit as xy goes to 0, 0 of x squared plus y squared over x to the 4th plus y to the 4th. So do you think this limit exists or doesn't exist? I'm sorry? Doesn't. Okay, so give me 2 paths that have different values, or give me one path that gives you plus infinity. So what are our go-to paths? Yes?
You plug in 0, like you do plug in 0 for y.
Yeah, so the first possibility is, let's just go along the x-axis. So if I go along the x-axis, I get x squared over x to the 4th. So the path y equals 0, that's now just the limit as x goes to 0 of x squared over x to the 4th, which is the limit as x goes to 0 of 1 over x squared, which is infinity. So we've already found a path where it breaks down. Could I look at the path x equals 0? Sure, but there's no need. This is already sufficient to prove that the limit doesn't exist. Okay? Any questions on this one?
Wait, could you just say again why?
So I'm choosing a special path. I'm choosing the path y equals 0. So I have to consider all possible paths, but if I can find one path where the limit doesn't exist, I'm done. Or I can find 2 paths that have different values. So since I have one path that has it does not exist, we're done. So limit People often write D and E for does not exist. Okay, so let's try to look at another limit. So let's look at another one where we have xy going to 0, 0. Let's do x squared minus y squared over x squared plus y squared. So does this limit exist? What path should we try first? Bless you. What's a good path to try? Same thing. How many of you have heard of Pavlov? You know, with his conditioning experiments? That eventually when certain animals hear bell, they know what to do. When you see a limit, you should now be conditioned. Check x equals 0. Check y equals 0. Later in the semester, I will condition you on what to do when you see a product. All right, but for now, this is your conditioning. So let's take the path x equals 0. So if we take the path x equals 0, we get negative y squared over y squared. What's that limit going to be? Negative 1. Let's take the path y equals 0. Then we get x squared over x squared. What's that going to be? 1. That's already enough to be done. I'm having so much fun, I'm going to do one more. Let's do the path x equals y. If x equals y, what do we get? Yep. And what will we get? What will the numerator be if x equals y?
0.
And the denominator won't be 0. So this was overkill. But 3 paths, 3 different values. Limit does not exist. Right? So let's do another one. Let's do the limit as xy goes to 0, 0 of x squared, x to the 4th plus y to the 4th over x squared plus y squared. What should we do first? X equals 0. So we do the path x equals 0. I don't have to write the whole limit thing. I can do this one in my head. If x equals 0, I've got y to the 4th over y squared. What do I get with y to the 4th over y squared?
Y squared.
Y squared. And what's the limit of y squared as y goes to 0? 0. Let's do the path y equals 0. If I do y equals 0, now I have x to the 4th over x squared. What do I get? 0. Oh dear. So we have the same value. Maybe the limit exists. Let's try the path y equals a times x. Let's go along a line. Then this becomes the limit as x goes to 0 of x to the 4th plus a to the 4th x to the 4th over x squared plus a squared x squared. I can take the x squared, divide that into the x to the 4th, I'll get an x squared. So when the algebra settles, it's the limit as x goes to 0 of 1 plus a to the 4th over 1 plus a squared times x squared. And x is going to 0. What does that limit equal? 0. So we've now shown that the limit is 0 along all straight lines. Is this enough to prove that the limit is always 0? No. Are you getting more confident that it might be 0? So what we want is we want a technique that will allow us to handle a problem like this. So I'm going to teach you the polar technique. Oh, this is the problem. Okay, no, this is a different one. I can erase this. So remember, we've got to be able to handle a path like that. And you do not want to write down that path. Okay? This is the secret. This is the picture. If I were to have a coat of arms, this would be one of the things on it. I might put sweep the leg. I really will. So we have x, y going to 0, 0. In polar coordinates, x is r cosine theta, y is r sine theta. If x, y is going to 0, 0, what do you know about r and theta? So if x and y are going to 0, what must be true about r?
It's also 0.
Right, because we know r is the square root of x squared plus y squared. So r has to go to 0. What about theta? As x, y goes to 0, 0, r goes to 0, what about theta? Theta is free. And that's what gives you these monstrosities. Theta can do whatever it wants, but r must be shrinking. And the goal is to show that when we have a nightmare like this, that it doesn't really matter what theta is doing, as long as r is going to 0, we want to have an expression that we can then show is tending to 0. Okay? So we're going to now apply that to the problem we were looking at. But is everybody clear on the general idea? We want to pass to polar coordinates. We'll send r to 0, and then let theta be arbitrary. All right, so let's move this back. All right. So we're going to continue with our limit of x to the 4th plus 1. So the limit as xy goes to 0, 0 of x to the 4th plus y to the 4th over x squared plus y squared. And so when we make the polar substitution, this is the same as the limit as r goes to 0, theta is free, and then x to the 4th is r to the 4th cosine to the 4th theta plus r to the 4th sine to the 4th theta. And down below it's r squared cosine squared theta plus r squared sine squared theta. What's cosine squared plus sine squared? 1. So I can take the r squared and I can divide that into the r to the 4th and I'll get an r squared. And this becomes the limit as r goes to 0, theta is free, and I'll have r squared cosine to the 4th theta plus sine to the 4th theta. Okay. Hopefully this is progress. Let's think about cosine to the 4th theta plus sine to the 4th theta. What limit law would you love to use at this point? What does this look like you want to use? The product. The limit of the product is the product of the limits. Does this limit exist? Cosine of the 4th theta plus sine of the 4th theta. Does that limit exist as theta goes to 0? As theta does whatever the hell it wants. Theta doesn't go to 0. Theta does whatever it wants. Does this limit exist? No. If you take theta equals 0, you get 1. If you take theta equals pi over 4, cosine of pi over 4 is root 2 over 2. So we squared, we get 1/2. We then square that again to get to the 4th power, so we get 1/4 plus 1, so you get 1/2. So you have a different value for this if theta equals pi over 4 than if theta equals 0 or pi. This theta does not exist. Its limit doesn't exist. This initially might make you a little worried. How badly does this not exist? How many of you have ever played the game of bridge? All right, so in bridge, you often have to bid, and frequently the bid you need to make is not set in your conventions, and you have to lie a little bit. And you just hope you're not lying too much and your partner can figure out what you mean. Over here, what's the smallest value this would take on? How small could this be? 0. In fact, it's never going to be 0, but we know it can't be smaller than 0. Let's just get some range. This is at least 0, and it's at most what? At most, how large could it be? I don't care about the optimal value. Just give me some bound. So that is correct, but that's a little bit harder to prove, right? And then you would have to see me doing some calculus differentiation. I'm happy to do it, but you could make my life easier. What's a good upper bound for cosine to the fourth plus sine to the fourth? It's at most. What's a good bound for cosine to the fourth? How large could that be? It's at most 1. And how large is sine? At most 1. So their sum is at most. That's much easier for me to do, right? It's at least 0. It's at most 2. If you want, as a nice exercise, go back to calculus. Use critical points. Figure out the minimum and maximum value of cosine to the 4 plus sine to the 4. All right? We don't need to do that. So we know that our expression 0 less than equal to r squared cosine to the 4th theta plus sine to the 4th theta is less than equal to 2r squared. So this is called the sandwich theorem. So now the limit as r goes to 0, theta is free of 0 is less than equal to the limit as r goes to 0, theta is free of r squared cosine to the 4th theta plus sine to the 4th theta is less than equal to the limit as r goes to 0, theta free of 2r squared. Okay, well, what is the limit as r goes to 0 of 0? Just 0. What about the limit as r goes to 0 of twice r squared? What would that be? 0. So we know this quantity is sandwiched between two things that are both converging to 0. What must happen to this? It must converge to 0. And this avoids having to check all these terrible paths. We are allowing theta to be free, and we're just looking at the r dependence. Okay? Yes?
If r is going to 0, though, wouldn't that mean theta is going to 0 no matter what?
No. Because if theta is fixed, we're approaching 0 along a straight line, for instance. Or you could allow theta to be giving you some kind of spiral. Maybe you could take theta equals 2 pi over r. And then of course, if you do this, theta is getting larger than 2 pi, but we only maybe care about it modulo 2 pi. So you could play all these sorts of games. You could have strange spirals going on. Doesn't matter what theta is doing. And if you can show that the limit exists no matter how theta is behaving, then you've shown the limit exists. And what's very important is we do not have to show that this limit exists in here. And different paths will give you different values for that. And so you might have different rates of convergence. But at the end of the day, we're always going to have it getting closer and closer and closer to 0. All right, so I want to end briefly with something which hopefully you've seen from calculus, L'Hopital's rule. How many of you have seen L'Hopital's rule? Right. It is a great way to handle indefinites. So if f and g are differentiable, and the limit as x goes to x naught of f of x over g of x equals 0 over 0 or infinity over infinity, then the limit as x goes to x naught of f of x over g of x is the same as the limit as x goes to x naught of f prime of x over g prime of x. So the limit of the quotient is the limit of the quotient of the derivatives. This only works if you have 0 over 0 or infinity over infinity. If you have 5 over 5, it doesn't work. If you have 5 over 7, it doesn't work. Fine. If I have 5 over 5, I know what the limit is. What's the limit? 1. If I have 5 over 7, I know what the limit is. What is it? 5/7. I only need L'Hopital's rule in situations where I don't know the answer. So here's a nice exercise. Let's look at the limit as x goes to infinity of x over e to the x. What does that expression look like? Is this a 0 over 0 or infinity over infinity? It's infinity over infinity. So by L'Hopital, I take the derivative of both, and I get the limit as x goes to infinity of 1 over e to the x. And what will that be? 0. So this is telling us that the function e to the x, the exponential function, is growing faster than the function x. If you really make it as a mathematician or a scientist, your name becomes a verb. And you can talk about L'Hopitaling something. Okay? If I gave you x squared over e to the x, what would you do? So if I gave you x squared over e to the x, what would you do? You would L'Hopital it twice. If I gave you x to the 2018 over e to the x, what would you do? You'd L'Hopital it 2018 times. And when the dust settles, you get 2018 factorial, which is big, divided by e to the x, which is bigger. And e to the x will go off to infinity, and you'll see that e to the x beats x to the 2018. We have time for one more example. What is the limit as x goes to 0 of the sine of x over x? Actually, maybe I'll write it over here. So any thoughts as to how we would do that one? Sine of x over x. What do we do? You'd L'Hopital it. What's the derivative of sine? Cosine. Derivative of x is 1. I'll take the easy one. What's cosine of 0? 1. What's 1 of 1? 1. 1 over 1? 1. Everybody agree with this? Okay, why not?
Wouldn't this go to 0? Because x is getting really large and it's just
No,
oscillating.
x is going to 0.
Oh, I'm sorry. I thought x was going to 0.
Nope, x is going to 0. Does this seem reasonable? It's correct, but you're doing something subtly wrong. And I want to point out whenever you might be in a situation where you are doing something and not realizing it. So how do you know the derivative of sine is cosine? Well, we look at the limit as h goes to 0 of the sine of 0 plus h minus the sine of 0 over h, right? That's how we calculate the derivative of sine. What's the sine of 0? So this is the limit as h goes to 0 of the sine of h over h. That's exactly this limit with the letter x replaced with the letter h. So how do I calculate this limit? I use L'Hopital's rule. And how do I know the derivative of sine is cosine? Well, I use this limit. Right? That's not legal. You need to somehow figure out what is this limit. This is the hardest limit in trigonometry. All of trigonometry comes from this. All of differential trigonometry comes from this. And in fact, the fact that we want this limit to be 1, that's where pi comes from. We want the derivative of sine to be cosine. We want the derivative of cosine to be negative sine. If we don't use radians, if we use degrees, you have these painful factors of 360 over 2 pi. So I'm going to just state something which we will get to much later in the semester. E to the I theta is cosine theta plus I sine theta. And this gives you, if you take theta equals pi, one of the most beautiful formulas in mathematics, e to the I pi is negative 1, and it's either I is or I am the square root of negative 1. We will see later in the semester how you can derive every trig identity from this. How many of you remember your double angle, half angle, triple angle formulas? There's a way to get all of them from this equation. And so I will show you later. Now again, this is the era of Google and the internet. It's not as big of a deal. You don't have to memorize as many things now. But it's nice to see how all the trig identities will come from this. And you'll get a sense of why is the derivative of sine at 0 equal to 1. All right, so this is a good place to stop.